So our first team is Shreya Mukherjee, and she's presenting on clean energy utilization for food production. So come on up here. I'll get your PowerPoint all set up. Hi. This is all you. Right there is advance. Should be good.
Thank you. So, good evening, everyone. From now on, I'll advocate on using clean energy for food production. But before I begin my story, I would like to show a brief study which shows how many of us are actually dependent on fertilizer based food production. So, what happened was the story began back in 18th or 19th century when it was predicted that there won't be sufficient space on earth to produce food for everybody. That is why people were researching on how to address this problem. And back in 1918, two famous scientists, Carl Bosch and Fritz Haber, found that ammonia can be synthesized from nitrogen and hydrogen, and this can be used to produce fertilizers which can enhance food production. So, in this topic, what we will be discussing is when we are using ammonia, is it sustainable? So, I'll compare in my presentation the current process which is used to synthesize ammonia, which is used for fertilizers, and how we are taking baby steps towards making the process sustainable. So, in the introductory part of my presentation, I'll say what kind of energy that is used for the synthesis of ammonia and how far it is based totally on fossil fuels and how can we use it, just air and water, to make ammonia. So the major thing is that ammonia is synthesized from two nitrogen and hydrogen. And the hydrogen mostly comes from natural gas and other fossil fuels. So 96% of all the hydrogen that is produced is based on fossil fuels. And 50% of that is used for ammonia production. So what if natural gas declines? Now, when that will decline, that can be debatable. But if it declines, we need to adapt some methods in which we can synthesize ammonia so that we can sustain our life. So the idea is, can we eliminate the use of hydrogen to create a backup of Haber-Bosch process? So what we are going to do, we are using an electrochemical synthesis of ammonia, wherein we just want to use air, water, and renewable electricity to generate ammonia in small scale, which can be used for on-site use in fertilizer production. I'll not go into the details of electrochemical synthesis right now, but what we are doing is we are using a reaction, which is a reduction reaction, wherein we use electrochemical energy and we use renewable electricity and convert it into a chemical, which is ammonia. So we are reducing nitrogen and synthesizing ammonia. But the process happens in this section, which we call cathode, and the reduction, and we are basically developing material in the cathode, which will facilitate the reaction, which we call catalyst. So in the next slide, you will see how actually this reaction happens. So nitrogen is shown by the blue balls, and when we supply the electrical energy, the renewable energy, the electrons will transfer through a conductor and through a catalyst, and the nitrogen will react with the electrons and the water present in the system and form ammonia. This is what we desire. So the desired reaction is nitrogen from the air will react with water in the system and consume 6 electrons to form ammonia. But along with that, we also have another reaction which happens on the surface of a catalyst, which is the water in the system will react with the electrons, will absorb the electrons and give hydrogen, which we call the hydrogen evolution reaction. So the major challenge of our work is the hydrogen evolution reaction. If the hydrogen forms, it will take the sites from the catalyst and then ammonia synthesis will be prevented. So our basic task is to develop the catalyst so that we can increase the selectivity of this whole ammonia synthesis process. So this is how our catalyst looks. It is disordered carbon, which is synthesized from a three-dimensional metal organic framework. So basically, a metal is bound to different organic ligands, and when we heat the metal over its melting point, the metal vaporizes, but the three-dimensional structure remains, and it forms disordered carbon network with porous cage with high surface area that will absorb the nitrogen. So far we have been able to synthesize around 10 to the power 9 moles per second per milligram catalyst. So this is how we quantify how much ammonia is synthesized. So what basically the right figure shows, it's taken from a recent review in 2019. What basically this figure shows is what is the difference in order of magnitude with different types of materials used as catalysts for nitrogen reduction. So where we stand is we have 10% current efficiency, but our catalyst is free of any precious metal. A catalyst is only carbon based. And we have reached an order of 10 to the power minus 9 mole per milligram per catalyst per second. Or if you take in terms of per unit area, we have reached around the same magnitude. So the catalysts which are higher, more active than ours has 30% current efficiency, but they are mostly based on precious metal like ruthenium and gold. So if we see about the economics of the process, we can see that the capital cost and the maintenance cost is not is much lesser than the Haber-Bosch, but the problem is the electricity cost. So if we are using only 50% of the energy can convert into ammonia. So right now on the results that we have, it will cost around $1.8 per kilowatt per hour. But if we can increase the efficiency, the higher we increase the energy efficiency, the economically it will become more economical. And the other things that is there in the analysis is the cost of the membrane and other cost of other capital costs. So this we are thankful to NREL for doing all these calculations for us. And we are kind of hopeful here because to start with, the price has gone down for both wind power and solar power. If you compare from 2019 to 17, there is a sharp decrease in the cost. So we are hopeful if we can optimize our catalyst further, we can make this commercial at least in a small scale. So with that, I'll end this presentation, and I would like to thank, first of all, my group, my advisor, my friends who are here and who have helped me in all my research, and of course, my parents who have supported me all the way. Thank you so much.
We did go over a few minutes, so I'm going to cut into the question time. So I'll allow for 2 minutes for judges' questions.
So your catalyst is metal free, but you need MOFs, which have metals to make the catalyst. So is it actually metal free, or are those metals in the MOF not consumed when you're making the catalyst? Or I guess I'm confused by the terminology of metal free, because you need metals to make the carbon.
Right. So there is metal in the precursor, but in the final catalyst, there is no metal. And the metal that is there in the precursor is zinc, which is not an expensive or precious metal. And the metal ratio that we use is only like 1/5 of the total.
So question in terms of the connection to kind of clean energy. I just want to make sure I'm understanding, and I very much appreciate the different way of creating ammonia and ammonia synthesis through this process. The connection here, I just want to make sure is, if I'm understanding correct, is instead of using natural gas to be able to make that synthesis, you're just suggesting using clean and renewable sources to work through that. not to create that clean energy or anything, but actually just being fueled by a renewable or low carbon solution. Is that correct?
Right,
Okay.
right. And the other thing is that the commercial process is at high temperature and high pressure reaction. So the Haber-Bosch process, which I was talking about, uses around 400 degrees C and 200 bars of pressure. But we are doing it at room temperature and atmospheric pressure. So it's renewable energy, ambient conditions, and SOx free. But yeah, the way you said, it's utilizing renewable energy rather than creating any clean energy.
Thank you. Thank you.
Can I ask one more? So you framed this around fertilizer production,
Correct.
but the end product of what you presented was ammonia.
Right.
So my question is, I just am ignorant to how fertilizer is produced. So is the
Right.
energy intensive step the making of ammonia, or is it the making of the fertilizer?
It's energy intensive step of making of the ammonia, because like 90% of the ammonia is used in the fertilizer production and the rest is used for other specialty chemicals.
And the process of going from NH3 to whatever salts or whatever we're using for the fertilizer is easy.
Yeah.
Okay.
It just mixes with sulfuric acid and forms ammonium sulfate
Okay.
or nitric acid and
Okay.
forms ammonium.
Thanks.
Thank you.